Alright, this time we're doing a paired sample t-test. This is when we have two samples that are coming from the same individual. So I have one individual that's giving me two different data points, or something similar to like to that, where the samples have this one-to-one relationship with each other. For this situation, we have somebody who's wondering if squirrel blood pressure is affected by sugar intake. So she gets 10 squirrels. She's got this big pile of candy, and she measures their blood pressure before and after eating this candy. Then she's testing this hypothesis against the significance of alpha equals 0.05. Here we need to assume that this difference in blood pressure is normally distributed because our sample size is less than 30. Alright, so this is the data we get over here. We've got a before and after column, and these all match up, so each row represents the same squirrel. This last column is the difference between the two. So if this is my x sub 2 and my x sub 1, or excuse me, if this is x sub 1 and x sub 2, this difference is going to be x sub 2 minus x sub 1. So the difference between these is 4, 6, and so on. The paired sample t-test at this point becomes a regular hypothesis test. Now that I have this data for those differences, I'm using that and I'm just doing a standard hypothesis test with it. As always, I want to determine my null hypothesis and alternative hypothesis. Here my point estimate is that difference. The null hypothesis is that the blood pressure wouldn't be affected at all, so the difference between the two would be 0. For this particular situation, the person didn't say that she thought it was greater or less than 0. So the alternative hypothesis is just that it's not equal to 0. Alright, so those are our two hypotheses. We have our data. Our point estimate is the average of our data, so the mean of that data, I'm just adding them all, dividing by 10. For this it comes out to be 3.5. I take the standard deviation of that. That's about 4.972. And my sample size is just 10. So to find my t-value, I take my mean, I subtract the null hypothesis, and I divide by the standard deviation of that sample mean distribution. So I'm dividing by my standard deviation over square root of 10. Crunch that out on the calculator and I get about 2.266 or 2.226. I want to compare that to my alpha, and again I need to switch my alpha to a t-value, or switch this t-value to a probability. My alpha is at 5%. My degrees of freedom is the standard n-1 here. My t-value for that particular alpha, and here I need to be careful. My alpha is 0.05. My alternative hypothesis isn't greater than or less than, it's not equal. So that changes how I want to do this. My alpha is 0.05. when I'm actually doing this test, now this is a two-tailed test. Since I'm not specifying greater or less than, I have to look at both tails, and that 0.05 gets split up between those two tails. So I need to see if this t-value falls in either one of those critical regions. My t-value is on the positive side, so we're kind of ignoring the left-hand stuff, and we're over in that side. So I'm not interested in the t-value at alpha. I'm interested in the t-value at alpha over 2. The t-value at 0.025 with degrees of freedom 9. It's about 2.26. So this is the t-value that determines my critical region. My t-value is 2.22, 2.23, so it's a little bit to the right of that. And for this particular case, I failed to reject the null hypothesis. I can also take this t-value, look it up on that chart, and convert it to a p-value. When I do that, I get about 0.053. That's not less than this alpha over 2, so again, I would fail to reject the null. Alright, so that's it for this one. If we wanted to do this again, we should take a larger sample, and we'd probably get better results and be able to reject that null.